Hi everyone and welcome back. We are officially in the last week of the semester, so after you're done watching this video, you never have to watch a video of me ever again, which will probably be very nice for you. The topic for today's lecture is going to be interpreting statistics that you might encounter out in the world. So in the news, on social media, just hearing friends and family talk about what they saw in the news or on social media, what you might read if you're reading something for class. There's statistics really everywhere. So much of our lives are built around knowledge that comes from statistics. So it's so important to be a good consumer of them. And if you take nothing away from this class, I really hope that you take this lecture away. Before I get into the lecture though, I just want to go through some reminders about the end of the semester along with some general announcements. So looking at the schedule, we're in our last week here. That's the lecture title. One thing I'm going to do, is I had some requests for this from a couple of people emailed me. I'm going to make that review Q&A slot that I have on Wednesday at 2:30 be a more formal project info session this week. So if you have questions about the project that you want to ask me in person, I'll be there as usual, but I'll be there sort of specifically with a mind to talk about it. If you're not free during that period, which is the Rutgers free period, also feel free to email me and we can set up a meeting one-on-one. If enough people come to the Wednesday one, I'll record it. If not, I think it's weird to record with only like a couple people in there. So I'll play that one by ear. But either way, I am going to be making sure to set aside some time to talk to anybody who has questions about what to do. I've assigned projects like this in previous semesters where we've been in class, and in my experience, there's usually some people who just have questions or want to talk through what they're doing there. I will also say, even if you don't do either of those things, feel free to reach out if you have any questions about the format or the structure or what you should be doing or what the different things mean. That's why I'm here. I'm always happy to answer those sorts of questions if you have them. And I'm going to talk a little bit more about the reminders related to the project and the info session on the next slide as well. But that'll be this Wednesday at 2:30. So also this week, as usual, problem set 13 will be due on Sunday if you choose to complete it. After this week, it'll be finals week at Rutgers in general. There's no final for this class that you have to sit for, but we do have the report for the project that will be due on May 12th. As a reminder, your lowest problem set grade will be dropped. So there are 13 problem sets in all. As you can see, we have problem set 13 coming up this week. Only 12 of those count towards your final grade. So if you complete all 13, I will drop your lowest grade. If you only complete 12 of them, those 12 grades will be the ones that count. Also, as a final reminder going into the end of the semester, this is what the grading scale looks like. It's based on points that correspond to these percentages. So you can go in Canvas and you can see how many points you have and then get a sense for how many points you'll need on the project to, get into whatever grade bracket you're aiming for. And also feel free to email me if you have any questions about that. Questions about, for example, what you would need to score on the project in order to get an A or a B or whatever. I'll generally can give you answers about that pretty quickly if you reach out to me. So this is just general end of the semester stuff. More specifically, I also want to talk a little bit more about this project info session and some reminders about the project in general, just since this is a newer thing that we're doing compared to, the sort of usual rhythm of the semester. All right, so reminders about the project and how it works. There are 4 options on Canvas that you can choose for the project. So if you've poked around at all in that module on Canvas yet, you'll see that there are these 4 options. Each of them involves a different kind of hypothesis test. So depending on which question you choose, you'll be either doing a t-test, an ANOVA test, a chi-square test, or looking at a correlation. The specific instructions for the project can be found on that assignment sheet that's also in that module on Canvas. So it talks through, what I'm looking for in the report, what you should do, what the data is that you're even looking at. So that's all written out there, and I definitely encourage you to take a close look at that. And then for the project, what I want you to do is just use the information that's on Canvas, so that assignment sheet, and then also the information you can download for each of the project options to write up a short report. And as I said last week, this project is based on real data, so it's data from a survey that you can download online. And it's a nationally representative survey of the United States, so when you do a hypothesis test using this sample, you can apply the results to the United States as a whole. On Canvas, for each of the options, you can download the corresponding sheet. So if you choose option 1, you can download that Word document that's titled, Project Option 1. And it'll tell you about the variables that you're looking at and how they are coded in that General Social Survey, or the GSS, which is where the data comes from. It'll also give you descriptive statistics and results from the hypothesis test. So part of your job will be to think about what the variables are and figure out which hypothesis test you're looking at to begin with. If you have any questions about that, though, of course, feel free to ask me. So once you have the information on Canvas, you'll have everything that you need to write up the report that will be answering this research question. So the sections on the report, which you can find in more detail in that assignment sheet on Canvas, will be to describe the research question, describe the variables that you're using to answer the research question, give some descriptive statistics about what the variables look like in the survey, and in that specific sample, then use the sample to do a hypothesis test that can tell you about how those variables might be related in the US population, and then briefly talk about a limitation to your conclusion about those variables. For the report, you'll notice in that assignment sheet that for each section that's laid out, there are a very specific set of things that are being asked for. To write up the report, I strongly recommend that you just take each of the section headings that are in the assignment sheet and answer, fill them out with the very specific things that are listed on the assignment sheet, and you'll be fine. So for this, I'm not looking for, a big essay. I'm not looking for anything beyond what is asked on that assignment sheet. So it's meant to be sort of technical writing. It's looking at these statistics and then interpreting them to answer a research question, and you'll be interpreting them based on what I'm asking you to tell me in the assignment sheet. But that said, I know that hearing me say all of this now without actually being able to look at it and have a conversation about it might make it hard to think about exactly what I'm looking for. So if you have any additional questions, I strongly recommend that you come to this info session that I'm going to have this Wednesday during the records free period, where as usual I'll be on Zoom, but I will be on Zoom specifically expecting to answer questions about this project and what I want you to do. And if you have any questions about what the GSS is or the survey is or how to interpret the stuff that you see on Canvas, anything that you might want to ask, please come and just ask me, or if you can't come, of course, also shoot me an email, or feel free to set up an appointment to talk one-on-one. Whatever you want to do. So as I often say for things like this, the hard part of this assignment should not be figuring out what I'm asking you to do. So please, if you have any questions whatsoever about what I'm asking you to do, just ask me. So I will hopefully see some of you on Wednesday. If not, I will hopefully talk to you over email or during some office hours appointment. Or if not that, I hope that you see what you're being asked to do and it makes perfect sense and you're very comfortable with it, and you enjoy doing the project and have a good rest of the semester and summer. But if that last one is not the case, please just either come to the info session or reach out. All right, so that's it for my end of the semester reminders. And now I'm going to get into this final lecture here. So this, of course, is a phrase that you might hear people say sometimes. There's lies, damn lies, and statistics, right? Meaning that statistics can be used and twisted and interpreted to say all sorts of things. And it becomes really, really important to be a good consumer of statistics and to know what it is you're looking at and to be able to think about some of the ways that statistics might be used or misused. And this is so important because statistics really are everywhere. Anytime you turn on the news and you see, study finds this or that, you're going to be looking at some sort of results based on statistical information. Anytime you see something about the crime rate doing something, you're thinking about statistics, right? So statistics is just numerical information about the world, and we are truly, truly surrounded by it. And as I just said, it's often misused or misinterpreted. Sometimes on purpose, and sometimes because the people who are reporting it aren't necessarily great consumers of statistics either. And in today's lecture, I'm going to just talk about a couple of specific ways that statistics can be misused or misinterpreted, and I'll go into each of these in more detail, in the rest of the lecture. But they include random variation in some variable being treated like it's a meaningful trend, correlation or relationships between variables being confused for causation, and findings that are statistically significant, in other words, findings where a null hypothesis has been rejected, being treated as though they are really substantively or significant, or in other words, meaningful, when they're not. All right, so the first one here is this idea that sometimes a statistic will vary across measurements and it can mean nothing at all, even though oftentimes it will be treated as though it does. So let's take a look at what this means. I want you to just look at this information I'm going to show you here and consider how it might be possible. So this is true. If you look up the numbers, you can see that this is true. But the 2013 murder rate in Newark was almost double the 2002 murder rate in Newark. But the murder rate in Newark has been about the same from 2000 to 2020. So how is it possible that we had the murder rate double from 2002 to 2013, but also stay the same for the last 20 years? The answer is something that's called regression to the mean. And what regression to the mean refers to is the idea that when you have some sort of variable where there's random variation in it, like the number of murders in a year, each time you measure it, it's going to be a little different just by chance. So even if overall the amount of crime in Newark is staying the same, some years you're going to have a little bit more crime just sort of randomly. Some years you're going to have less crime sort of randomly, even if crime isn't meaningfully changing in any way. Like you're just going to happen to have differences in how much crime is measured in a given year. And a result is that something like a murder rate is going to be higher in some years and lower in some years, even if it stays about the same on average. And so what happens is that some years it goes up, but then it generally comes back down to its average or typical value. Some years it's going to go down, but then it's going to come back up to that average or typical value. And it's going to go up and down, but it's going to just wiggle around one particular value. When this happens, if you compare a year in which the value of the variable was measured at a very high point to a year where that value is measured at a very low point, it's going to seem like there's a dramatic change. But what's really happening is something like this, where the murder rate has been about the same. So it wiggles, it goes up a little bit. There's just randomness involved in that. Some years more crime is just going to happen randomly. Some years it's going to happen less. There's not really any particular reason for it. Variation can be either a result of measurement, so maybe more crimes got recorded in one year and less got recorded in another year, or it's just going to have to do with sort of the randomness in the amount of crime itself. So if there's just happened to be more fights that resulted in a homicide in one year than in some other year. But either way, you have a generally pretty stable murder rate with random variation. But if you measure it in a year where there just so happen to be very few murders, and you measure it in a year where there just so happen to be a lot of murders, and then you compare only those two data points, you end up with what looks like a really, really dramatic difference. And so in the case of murder in Newark, 2002 was a year in which there just so happened to be relatively few murders recorded, and 2013 was a year where there just so happened to be a lot of murders recorded. And 2013, this count was almost double 2002's count. But it didn't mean that crime was rising dramatically in this time period. Instead, it just means that you happen to catch it in a low year and you happen to catch it in a high year. Where this comes up all the time is that when you see changes in things reported in the news or reported by police officials, for example, you often see a lot of emphasis on change from one year to another year, or comparing just, one point in time to another point in time. And so instead of looking at overall trends, people pick out these 2 years, so 2002 and 2013, and say, wow, crime is skyrocketing. It's gone from 2002's rate to 2013's rate. Like, we should all be very concerned about this skyrocketing crime. When in reality, that's not what's happening. And so the moral of the story here is that when you're considering trends, when you're considering whether something's going up or down over time, you don't want to rely on only 2 data points because they can't tell you a lot about what's happening. And they can't tell you whether you're looking at something that's actually increasing or decreasing, or whether you're just happening to, catch something that was measured at a high value or measured at a low value, even though there's no real meaningful change in that trend. And an example of this is this billboard that I actually used to drive by on my way to work, and it drove me crazy every single time. So this was put out by the New York State Correctional Facilities Union, I think, or I guess New York State Correctional Officers and Police Benevolent Association. And they're trying to make the point that assaults on correctional staff are skyrocketing, right? They're up 55.1%. But this statistic, scary as it looks, is not really all that meaningful. Why? Well, we don't know what the rate is to begin with, and we don't know whether, this change that we're looking at is part of just a general wiggly line that's staying flat. And it just so happened to be a year where there were more assaults, and next year we'll be right back to the normal, and maybe the year after that it'll be one with a lower number, and then right back up, and doing the same kind of wiggly flat line thing that most statistics do when you measure them repeatedly. But by just focusing on this single increase, right, from one point in time to a second point in time, you're painting a picture of something that really just doesn't give us a whole lot of information about what's going on. And so, based on this, it could be that assaults were going up and that it's, some trend where it started low and it's getting higher and higher and higher. Or it could just be that you happen to pick a year with a relatively few assaults, you happen to pick a year with relatively high assaults to calculate this 55% statistic, and normally we'll just be kind of somewhere in the middle, and it'll be varying around that average value. Right, so that was our first one there, the idea of regression to the mean, where if you measure a statistic over and over again, it's probably going to be different each time just by chance, either because of how it's being measured, so for example, how the crime statistics are being recorded, or just because of random variation and other things that are going on that's causing it to be, high or low, and it doesn't really mean anything. But it's not actually going up or down in a meaningful way. It's staying about the same with a little bit of, variation around that point. The next topic I'm going to talk about is the idea of correlation versus causation. You've probably seen this before. I think this one has sort of almost made it into meme status in the world, the idea that correlation is not causation. But I want to talk about what it really means and what it means when you look at different types of variables that might be related. The first way in which correlation is not causation is when variables are related in a way that is spurious. So a spurious relationship between variables looks like this. You have some variable z that causes some variable x. This variable z also causes some variable that we call y. And variable x does not cause variable y, but because they're both caused by variable z, they're going to be related to each other statistically. So if you were to, for example, calculate a correlation for variables x and y, they would be related to each other, even though one of them, isn't causing the other one. And until you manage to account for that variable z, so until you somehow control for it statistically, it'll look like your variables x and y are correlated. So here's the classic example. There is a correlation between the amount of ice cream people eat and how many shark attacks there are. So one of our variables is eating ice cream. The other variable is being attacked by a shark. So we'll call those variables x and y. So x and y look like they're related, right? If you do a scatter plot of the pounds of ice cream eaten and number of shark attacks, you're going to see a relationship where the more ice cream is eaten, the more shark attacks there are. But does this mean that people are being attacked by sharks because they ate ice cream? Does it mean that people eat ice cream and then, it's a little harder to swim, maybe you're just full, you can't get away as fast, so you're going to get attacked by a shark? No, right? So instead what's happening is that you have this third variable that we call variable z, in other words, a confounding variable, that's causing both of them. So where you have higher temperatures, so seasons where people are doing more swimming and eating more ice cream, you're going to have, more swimming and more ice cream. So instead of saying that ice cream sales cause shark attacks, you would say that there's this other variable that's causing ice cream sales and this other variable that's causing shark attacks, and it's making it so that they're related to each other statistically, even though they're not actually meaningfully related to each other. And if you were to take into account higher temperature, so you could do this statistically, or you could say just look at one season, right? So you only look at these things in the summer when the weather's, in the same temperature range. You wouldn't see a relationship between those things anymore. So instead, the fact that both of these things are caused by higher temperature is making it look like they're related when really they're not. And there are other examples of spurious relationships as well. So statistically, there's a relationship between the number of churches in a city and the number of bars in a city. Does this mean that churches cause bars to come, or that bars cause churches to come? Well, neither, right? And the idea is that the bigger a city is, the more population it has, and the more churches there are, and the more bars there are. So your variables are x and y, are churches and bars, and then that variable z, that common caused or confounding variable, is the population of a place. But if you were to only look at churches and bars, you'd see that they were related, because you'd see that as the number of churches increases, the number of bars also increases. So they'd be positively correlated. And that correlation would exist until you accounted for the amount of population in a particular city. But what you wouldn't want to do would be to look at the correlation between churches and bars and assume that one of them was causing the other one. Another example would be the number of speeding tickets that somebody has gotten and the number of accidents that they're in a car. So number of speeding tickets is positively correlated with the number of accidents. Does this mean that the more speeding tickets you give somebody, the more accidents they're going to get into? If you give somebody a speeding ticket, they're going to be so angry they're going to drive into a tree? Probably not. And instead, both of these things are going to be related to the number of miles that somebody drives in a year. So the more you drive, the more likely it is you're going to get a speeding ticket, and the more you drive, the more likely it is that you're going to be in an accident. So number of speeding tickets and number of accidents are spuriously related to each other because they're only related through this other variable, which is the number of miles that you drive in a year. And one final relationship, or one final example of a spurious relationship would be height and reading ability. So if you're looking at kids in elementary school, there's a relationship between how tall they are and how well they read. Does this mean that being taller causes kids to read better? Well, no, of course not. Instead, what you're seeing is a relationship that's caused by their age. And age causes kids to be taller, and it also causes them to read better. So when you don't account for kids' age, you would see a relationship between height and reading ability. So one thing to think about, oh, I got one more example. And then I'll say what your one thing to think about is. So this is pulled from an actual description of study abroad programs put out by some college, where they're trying to convince students to sign up for study abroad programs. And they make the point that if you participate in a study abroad program, you're 19% more likely to graduate on time. See a rise in GPA. You're more likely to be accepted into your first or second choice of graduate school. So many study abroad students find employment, right? So many study abroad students find that they're satisfied with their jobs. Well, what's the problem with this? We're looking at two variables here, which are participating in study abroad programs and then like general success in life afterwards. Does this mean, though, that participating in study abroad programs causes people to be successful in graduate school or work? And the answer is no. And instead, it's much, much more likely that there are other variables that are both causing students to participate in study abroad programs and causing them to do well in life later. So one of those variables might be, drive or motivation. If you're a student who manages to get your way into a really good study abroad program, you're probably somebody who's also going to take initiative and do well in work later. But then there's also the issue of access to resources, right? And if you're a student who is able to get into a study abroad program and say pay for it, you're probably also a student who's going to have more resources that will help you go to grad school or get a good job later. And so there are these other variables that are sort of lurking there that if you're only focusing on participation in study abroad programs and success afterwards, you're not going to be getting the whole story. And so it's wrong to conclude based on this that studying abroad makes people do better in life afterwards. And instead, it's much more likely that, students who are well positioned to succeed in life are also well positioned to study abroad. So the moral of the story is to really think critically about spuriousness when you see statements about one variable causing another one. So it's always a good idea to think, when you see something like this, the whole thing about study abroad here, does it really make sense that studying abroad is going to cause people to do better in life? Or is it more likely that people who are able to study abroad are also going to be generally able to do better in life? All right, so I also want to talk about another way in which two variables may appear to be related, but there is a third variable involved that really changes what the nature of that relationship is. And specifically, we're looking at what are called direct versus indirect effects. So a direct effect is when one variable causes another variable. An indirect effect is when one variable causes a second variable, which causes a third variable. And so a direct effect is pretty straightforward. One variable is the cause of the other variable. If you look at them, they will be related to each other, and there will be a causal relationship there. With an indirect effect, though, it gets a little bit trickier. Because if you're looking at all three variables, you'll be able to see the way that, variable A causes variable B, which causes variable C. But if you're only looking at variable A and variable C, you're going to see that they're related to each other as well, and they'll be related to each other through this other variable that you're not looking at. So we have this indirect effect that occurs when one variable causes another variable, which causes a third variable. And then so you have your first variable being related to your third variable, but only through this other variable. So similarly to thinking about spuriousness, if you're only measuring variable A and variable C in this example, you'll see that they're correlated to each other. But this doesn't necessarily mean that they are related to each other, in a direct and meaningful way. So I'm going to talk about some examples I think that will help to explain what this means. So if you're studying elementary school students, you might find that students who need glasses but haven't gotten glasses yet don't do well in elementary school. So this would be a correlation between these variables of needing glasses and not doing well in elementary school. Does this mean, though, that needing glasses is somehow inherently related to school ability or doing well in school? Well, probably not. And instead, there's a third variable in there that is linking these two indirectly. So instead, needing glasses might mean that a student can't see the board or see what the teacher is doing, which would lead to poor performance in elementary school. But if you're not thinking about that intervening variable that causes that indirect effect, which is not being able to see the board, you might be making bad conclusions about the relationship between eyesight and school ability. Another example might be a relationship between somebody's income and their weight or health. So these things are correlated, but does it mean that income has anything to do with somebody's physical body? Well, not directly, but indirectly you might see a relationship between someone's income and then their access to good nutrition or time to exercise or other things that go into weight and health that would then lead to that outcome of weight or health. So when we're thinking about direct versus indirect effects, we're thinking about one variable that sort of starts a chain that leads to another variable that leads to another variable. And if you don't look at what's going on in the middle, you're going to see a correlation between your variable at the beginning of the chain and your variable at the end of the chain. But it would be incorrect in that case to assume that there is a direct causal relationship between your first variable and that variable at the end of the chain. So eyesight doesn't have anything to do with school ability, unless those things are connected by an ability to see what's going on. Income doesn't have anything to do with physical weight or health, unless those things are connected by access to good nutrition or time or ability to exercise or other things that link them up in that chain. And an example where this becomes really, really relevant is when you're looking at relationships between people's race and other outcomes. So this is an abstract from a paper where somebody was looking at the relationship between race and SAT scores in California. And what they found is that a lot of the variation in SAT scores can be predicted by factors known at students' birth. So those things include SES, so socioeconomic status, like family income, parental education, and also race and ethnicity. And they found that among these, race has become the strongest predictor of SAT scores. So somebody might look at this and incorrectly assume that race has something to do with, SAT performance or ability. But what they would be missing is that, somebody's race affects the extent to which they are affected by racism at a lot of levels. So that's sort of societally in terms of the resources available, the education system that somebody's likely to end up in, discrimination sort of within school, but also in the testing procedures themselves, and all these other host of things that are downstream from race that then affect SAT performance. And this is the case when you're looking at other things too, like crime or victimization, where somebody's race doesn't inherently have anything to do with these outcomes, but it's connected through this chain and linked through the various ways in which racism in society benefits white people and disadvantages people of color. So the takeaway here would be that race isn't directly related to SAT scores, but it affects the ways in which people have different resources, opportunities, experiences with discrimination and so on, which then affect SAT scores down the line. So when thinking about direct versus indirect effects, we wouldn't say that there's spuriousness because, in this case, discrimination is not causing somebody's race, but rather it's that intermediate link in the chain between race and then, whatever outcome you're measuring. But because there's that indirect link in the chain, it means that if you only look at the beginning of the chain and the end of the chain, you would incorrectly come up with a relationship about how one causes the other if you're not considering all those intermediate steps. So the moral of this story is to also think critically about direct versus indirect effects when you're thinking about two variables being related and then thinking about whether one might cause the other one. And so for this correlation versus causation segment here, depending on which of the project options you choose, you might want to think about whether your variables might be spuriously related or whether there might be some intermediate steps between your variable that would be your independent variable and then your variable that would be your dependent variable down the line. All right, so that's one way in which variables should be, and relationships between variables should be interpreted with care. Another thing that I want to talk about, and what I'll close out this lecture with, is the idea of significant findings. All right, so when we talk about statistical significance, what we are referring to are findings from a sample in which the null hypothesis is rejected. So if you're looking at relationships between variables or comparing means or whatever it is you're doing, you would say that the relationship between the variables or the difference in the means is statistically significant if we reject the null hypothesis. And that's literally all that statistically significant means. It means that the null hypothesis has been rejected. And a result of this is that when results from research are reported, findings are generally treated as if they count if p is less than 0.05. And so anytime that p-value dips below 0.05, there's a tendency to talk about the findings as though they are really meaningful and that they sort of tell us big things about the relationships between those variables. The problem with this, though, is that when you have an alpha level of 0.05, which is the standard in social science research and many other disciplines as well, the amount of information that you can get from statistical significant findings is not always what it's thought to be. So one reason for this, and one reason that statistical significance should not always be treated as meaningful, is that a relationship might be statistically significant even if it isn't that large or that meaningful. So one reason for this is that relationships tend to be more likely to be statistically significant, so it's easier to reject the null hypothesis in most significance tests if you have a larger sample. So if you have a large enough sample, you can detect really, really small differences in means or really, really small relationships between variables, and they'll pop up as statistically significant, even if they're not that large or that meaningful. But this is an issue that if somebody is a researcher, they can account for, and they can try to really describe what the nature of the relationship is, rather than just whether or not it's statistically significant. As a consumer of statistics, if you see that, one thing is said to be related to another thing and it's statistically significant, it's good to think critically about what the nature of the relationship actually is and how big are the differences in means, or how strong is that correlation that's statistically significant. Another problem is that when you're looking at p-values to tell you everything you want to know about a relationship, you get false positives. And in significance testing, a false positive refers to when you reject the null hypothesis, even though the null hypothesis is true. Another term for this is a type 1 error, where the null hypothesis is true, but you reject the null hypothesis because your sample happens to be in that 5% of least likely samples where we're saying that we would reject the null hypothesis. And this happens because of the way that hypothesis testing is set up. So sort of thinking back to what we've been doing over the last couple of weeks here, we say that we reject a null hypothesis when our sample is in the 5% of least likely samples that you would expect to get if the null hypothesis is true. Put another way though, if the null hypothesis really is true, your sample is going to be in that least likely 5% of samples, well, 5% of the time, just by chance. And so you basically have a 5% false positive rate when you have an alpha level of 0.05. And this is referred to formally as a type 1 error, where the null hypothesis is true, but you reject it because you just so happen to get a sample that had extreme results. So there just so happened to be a big difference between means in your sample. There just so happened to be a strong correlation between variables in your sample. And even though the null hypothesis is true, you got this weird sample and we rejected the null hypothesis by mistake. And with an alpha level of 0.05, we're going to do that 5% of the time. As a quick note, there is also something called a type 2 error, which is the opposite of that. So a type 2 error is when you fail to reject the null hypothesis, even though it's not actually true. Or sorry, you fail to reject the null hypothesis when you should reject the null hypothesis, which I guess is what I just said, but I think that's a better way of saying it. So the type 2 error is the opposite of the type 1 error. With a type 1 error, your null hypothesis is true, but you reject it anyway. With a type 2 error, your null hypothesis is not true, but you fail to reject it. The reason that I'm not going to talk about the type 2 error as much here is that it's sort of less impactful for reporting of statistics because, well, when a hypothesis is not rejected, it's not treated as though it counts because p isn't below 0.05. So type 1 errors become an issue because 1 out of every 20 studies, so 5% of studies, is going to have a false positive just by chance if you're using this alpha level of 0.05. And so sometimes research where you've rejected the null hypothesis by mistake, in other words, where you have a false positive for some relationship that you found between variables or some difference in means, and those get treated as though they're real relationships between things. When thinking about false positives in hypothesis testing, though, there's not actually that much you can do about them because they're happening just by chance, and the way that the hypothesis test is set up, it sort of builds us into it, where whatever your alpha level is tells you how likely those false positives are, and you just have to expect that sometimes you're going to get a false positive. But one thing to think about here and one thing to take away is that if only one study shows a result, it doesn't necessarily mean that that result is true. And so it's important to look at patterns and findings and look at studies that really make an effort to not hinge everything on a single hypothesis test, because false positives are always possible. Even more concerning though, so a false positive, a type 1 error, is when it happens just by chance. But a more concerning thing that often happens in research, sort of intentionally or not, is something referred to as p-hacking. And p-hacking is when researchers use methods that make it more likely to reject null hypotheses and get, statistically significant results from their studies. And sometimes it's done in the name of, wanting to just do lots of tests and see what happens. Sometimes it's a little bit more malicious than that, or, you're aware that you need that p-value to be less than 0.05 for your research finding to be treated as though it counts. But in either case, p-hacking refers to using different methods to try to get a statistically significant finding that can then be reported to the world as though it's a finding that counts. And an example of p-hacking comes from this study here where researchers went out of their way to show that they could get statistically significant results, just by fudging with the data, and then they could report them. So in this study, they had people listen to different types of music, and then they calculated their age. They found that people who listened to When I'm 64 rather than Kalimba, which I think is elevator music, were actually younger than people who were assigned to listen to Kalimba. So this was a statistically significant finding. With a p-value of 0.04, They were able to reject the null hypothesis that people who were assigned to listen to one song were the same age as people who were assigned to listen to the other song. So they found a statistically significant difference in the age of people who were assigned in their study to listen to When I'm 64 by the Beatles versus people who were assigned to listen to this kalimba song. So a bad take on this would be that people who were assigned to listen to When I'm 64 were made to be younger than people who were assigned to listen to this other song. That doesn't make a lot of sense, though, right? So being told to listen to one song in a study is not going to make you younger than being told to listen to another song. Even though, with this great experimental design that they had, they were able to reject the null hypothesis that people who were assigned to listen to one song were the same age as people who were assigned to listen to the other song. But what they actually did was go through a whole bunch of different procedures that let them get this p-value just by fudging around with the numbers and doing different things. And so they had that right up there to show that, that could be what the study looks like when it would be reported in an article or reported in the news. But what they actually did was try a whole bunch of different things until they got a statistically significant result just by chance. So instead of having just one hypothesis test with a 5% false positive rate, they did so many different tests and did them so many different ways that they were essentially guaranteed to get a result that they were looking for just by chance. So this is an example of p-hacking, where researchers do lots and lots of hypothesis tests and do them in lots and lots of different ways in order to, get some result that comes out as being statistically significant because the p-value is less than 0.05. So this is a bigger problem than getting unlikely results just by chance, because this means that you can get unlikely results if you try enough things, then you'll be able to report those results as though they're meaningful. So the moral of this story is that even if you see that some finding is statistically significant, that the p-value is less than 0.05, that some null hypothesis has been rejected, it doesn't necessarily mean that that finding is meaningful. And it's important to dig deeper, both to look at what the relationship between the variables actually is, and then also to consider what the methods of the study were, and how likely it is that what you're looking at is a type 1 error, or in other words, a false positive, where some null hypothesis was rejected and a relationship was found between variables, even when that relationship didn't really exist. All right, so that's all I have for you in terms of content for this lecture. So for the last part of the project, where it's described as limitations, what I ask you to do is to talk about one way in which whatever relationship you see between your variables might not reflect a causal relationship between those variables. So here's where I want you to think about things that I've talked about in this lecture. I will tell you right now, I don't want you to talk about regression to the mean, because that refers to changes you see in a single variable over time. Nobody here is looking at a single variable over time, so that does not apply. But you can either talk about the ideas that we saw in correlation versus causation, or in this section on statistically significant findings. So depending on which variables you have for your project option, you might want to think about whether they could be spuriously related, or you might want to think about whether there might be some intervening variable in there. So an indirect effect linking your first variable to your second variable. You could also think about your findings in terms of, what are the chances of getting a false positive? Or is the relationship you see, even if it's statistically significant, is it substantively meaningful? So is it a big difference in means? Or is it a strong correlation? Or is it really a pretty weak relationship that might not be that meaningful, in really understanding the world? So I've been on this slide for a while now, so just as a reminder, I have this project info session that'll be during my sort of Wednesday Q&A office hours on Zoom at 2:30. Optional, but if you have questions about the project and you want a dedicated time to ask them, I would highly recommend dropping in during that time slot. If you can't make it, because I know a lot of you guys work and have other commitments outside of just the Rutgers schedule, please, please, please reach out to me over email or set up a meeting, whatever works best for you. And I will hopefully see some of you later this week. Otherwise, closing remarks here. I know it's always a weird semester when you're mostly communicating through video, and I've been here just talking to my laptop. You guys have been at home watching me talk to my laptop. And I'm sorry that I don't have more of a chance to interact with everybody. But that said, I have enjoyed my semester with you. I hope you guys have had a good semester as well. And if I don't see you before the end of the semester in some sort of face-to-face or email format, I hope you have a wonderful summer. And I guess a good rest of your life. All right, so again, reach out if you have any questions about the project or the problem set or anything else, and have a good week.